Okay, we're moving on with section 5.2, Newton's first law and inertial frames. Hopefully you've watched the video on reference frames. If not, I recommend, it's not required, but I recommend highly that you watch it. And we're going to move on with Newton's first law and inertial frames. Now, what you see here is a side view of a simplified air hockey table. Yeah, I'm sure you all have played air hockey. You've got the table with a bunch of holes, and a little plastic puck rides on top of the little air holes. As the air blows through the little holes, the hockey just slides on a seemingly frictionless surface. Um, so imagine the puck on a perfectly level air hockey table. The puck remains stationary when placed at rest on the table. From if you're an experienced air hockey table player, you know that it does kind of tend to move around because there are no perfect air hockey tables, but we're idealizing the situation. So uh, if there were no real forces, that would just stay in one position. Now, imagine that same hockey table on a moving train with constant velocity. If you're riding on the train, it would be perfectly still. It would remain stationary. Now, if the train were to accelerate, let's say it were to go around a curve, if it were to curve left, the puck would appear to go to the right. If it were to turn to the right, the puck would appear to go to the left. If it were to slow down, if the train were to slow down, the puck would appear to go forward. And conversely, if the train were to speed up, the puck would seem to go backward. So if the train accelerates, the puck would move in the opposite direction of the um, change in velocity. So let's look at this next slide. Recall that a moving object can be observed from any number of reference frames. Newton's first law of motion defines a special set of reference frames called an inertial frame. This reference frame, the inertial reference frame, if an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. Let me read that again. What does that mean? That means it's important. If an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. It's an inertial frame of reference. When the puck on an air hockey table is located on the ground, the inertial reference frame is just the ground. There's no horizontal interactions of the puck on any other objects, so it has zero acceleration. When you are on a moving train at constant velocity, you also observe you're on the train. You're observing the puck from an inertial frame of reference. Any reference frame that moves with constant velocity relative to an inertial reference frame is itself an inertial frame. When you and the train accelerate, you observe the puck from a non-inertial reference frame. You and the train are accelerating relative to an inertial frame of reference of the Earth's surface. And according to you, the puck appears to be accelerating. But the reference frame where the puck has zero acceleration, there is a reference frame where the puck has zero acceleration. The observer standing outside the train on the grounds sees the puck sliding relative to the table, but moving with the same velocity with respect to the ground as the train had before it started to accelerate. So Newton's first law is still satisfied even though your observations as a rider on the train show an apparent acceleration relative to you. So let's take a quick little quiz here. Oops, I should have been, I jumped the gun. Let's go back. No quiz yet. The reference frame that moves with constant velocity relative to a distant star is the best approximation of an inertial frame. And consider Earth as such a frame. Earth is not really an inertial frame because of its orbital motion around the sun and its rotational motion about its own axis. The centripetal accelerations are small compared with g. So we model the Earth as an inertial frame along with any frame attached to it. Before 1600, people believed that the natural state of matter was a state of rest. Aristotle taught that, well, it's the nature of things to come to a standstill, where Galileo, through some thought experiments, concluded that objects resist changes in motion. That is, if an object is not in motion, it'll stay in motion. If an object is rolling, its tendency is to continue rolling, and the only thing that causes it to slow down is friction forces. Galileo said any velocity once imparted to a moving body will be rigidly maintained as long as the external causes of retardation are removed. So a spacecraft drifting through empty space with its engine turned off will keep moving forever. We have some satellites that were launched when I was in high school that are still there. They recently, within the last 10 years or so, have reached the outer limits of our solar system, and they're still going. So let's have a practical statement of Newton's first law of motion. In the absence of external forces, let me move the slide. I'm sorry. In the absence of external forces, and when viewed from an inertial reference frame, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity, that is, with a constant speed in a straight line. Okay, when no force acts on an object, the acceleration of the object is zero. And the isolated object, that is one that does not interact with its environment, is either at rest and stays at rest or moving with constant velocity. We're going to define a term, inertia. Inertia is the tendency of an object to resist any attempt to change its velocity. So in other words, if its velocity is zero, it's going to remain zero. That's an object at rest remains at rest. And if the velocity is moving, it's going to resist any tendency to change its velocity. In other words, it's going to want to continue to move. An accelerating object must experience a force in order to accelerate. So we define force as that which causes a change in motion of an object. It causes a change in motion. That's either a change in velocity, either speeding it up, slowing it down, or changing its direction. So now it's time for the quick quiz. Which of the following statements is correct? It is possible for an object to have motion in the absence of forces on the object. It is possible to have forces on an object in the absence of motion of the object. Neither statement A nor statement B is correct, or both statements A and B are correct. So let's see. So both A and B are correct. Choice A is true because Newton's first law tells us that motion requires no force. An object in motion continues to move at a constant velocity in the absence of external forces. Choice B is also true. A stationary object can have several forces acting on it, but if the vector sum of all these external forces is zero, there is no net force and the object remains stationary. Okay, this ends our discussion of Newton's first law on inertial frames. Next, we will have a one-slide discussion of mass.